Water vapor from ambient air will spontaneously condense inside porous materials or between touching surfaces. But with the liquid layer being only a few molecules thick, this ubiquitous and important phenomenon has lacked understanding, until now. Researchers at the University of Manchester led by Nobel Laureate Andre Geim, who, with Kostya Novoselov, was awarded the Nobel Prize for Physics 10 years ago this month, have made artificial capillaries small enough for water vapor to condense inside them under normal, ambient conditions. The Manchester study is entitled Capillary Condensation under Atomic Scale Confinement and will be published in Nature. The research provides a solution for the century-and-a-half-old puzzle of why capillary condensation, a fundamentally microscopic phenomenon involving a few molecular layers of water, can be described reasonably well using macroscopic equations and macroscopic characteristics of bulk water. Is it a coincidence or a hidden law of nature? Capillary condensation, a textbook phenomenon, is omnipresent in the world around us, and such important properties as friction, adhesion, stiction, lubrication and corrosion are strongly affected by capillary condensation. This phenomenon is important in many technological processes used by microelectronics, pharmaceutical, food and other industries, and even sandcastles could not be built by children if not for capillary condensation. Scientifically, the phenomenon is often described by the 150-year-old Kelvin equation that has proven to be remarkably accurate even for capillaries as small as 10 nanometers, a thousandth of human hair's width. Still, for condensation to occur under normal humidity of say 30% to 50%, capillaries should be much smaller, of about 1 nanometer in size. This is comparable with the diameter of water molecules, about 0.3 nanometers, so that only a couple of molecular layers of water can fit inside those pores responsible for common condensation effects. The macroscopic Kelvin equation could not be justified for describing properties involving the molecular scale and, in fact, the equation has little sense at this scale. For example, it is impossible to define the curvature of a water meniscus, which enters the equation, if the meniscus is only a couple of molecules wide. Accordingly, the Kelvin equation has been used as a poor man's approach, for the lack of a proper description. The scientific progress has been hindered by many experimental problems and, in particular, by surface roughness that makes it difficult to make and study capillaries with sizes at the required molecular scale. To create such capillaries, the Manchester researchers painstakingly assembled atomically flat crystals of mica and graphite. They put two such crystals on top of each other with narrow strips of graphene, another atomically thin and flat crystal, being placed in between. The strips acted as spacers and could be of different thickness. This tri-layer assembly allowed capillaries of various heights. Some of them were only 1 atom high, the smallest possible capillaries, and could accommodate just one layer of water molecules. The Manchester experiments have shown that the Kelvin equation can describe capillary condensation even in the smallest capillaries, at least qualitatively. This is not only surprising but contradicts general expectations as water changes its properties at this scale and its structure becomes distinctly discrete and layered. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.